So we talked about several different 2-transistor stages, and we'll talk about another one today. But before we do that, let's talk a little bit about an example of a potential problem or typical scenario. So let's say you're trying to make an integrated radio receiver. You're trying to make a chip that goes into your phone or your device, and then it's a receiver that receives signal from the communication signals from the cell towers or radio or something, right? What is the characteristic of these signals, the radio signals that you receive? They are very small, right? Why they're very small? Because they're going over large distance. They experience R over, 1 over R squared losses and things of that sort. So you have a very small signal coming in, let's say arriving at your antenna, and then you're going through some traces, you're going to your chip, and then you are having an amplifier. So first thing you do is an amplifier, a low noise amplifier, LNA. And we talk about these later in terms of RF. But then let's say on the same chip you have some digital circuitry, which is very common nowadays. We do a lot of things with digital. And then there's a digital line passing by here. So this is a clock, let's say. A digital clock passing by. So you have a weak signal arriving at your antenna, and you have this big digital clock next to it. And it somehow couples to it. Somehow, maybe it may be electrostatically couples to it, maybe it magnetically couples to it, or maybe it couples through it through the substrate, that's the silicon substrate or something like that. So it couples through it somehow, right? What's going to happen to the signal? So you have this weak signal coming in. Let's say it looks like that, and then you have this big signal next to it. What is that going to do to your signal? You will see coupling, right? For example, with this thing, if it's capacitive coupling, you will see spikes like that coming. Every time the clock edge switches, you will see something like that. And of course, this is not a highly desirable thing, because now your signal has this undesirable element on it. As you amplify it, this will get amplified, and it goes through the system, and it can saturate your system. It can create all sorts of noise and errors if it's digital, things of that sort, right? So this is obviously not a good scenario. So what do we do? What can we do when you have a problem of this sort? And this is a general statement. When you have coupling problems, there are essentially 3 things you can do. So what are those 3 things? If you have undesirable signal bothering you, right? If there's some annoying person that is bothering you, let's say they're constantly talking and bothering you, what do? There are 3 things you can do. Say again? Filter. Okay. Filter. What do you mean by filter? So let's talk about filters. So I think you showed a different picture. Maybe we can start with that. We'll come back to filter in a second. So one of you guys did this. So one is that make yourself less sensitive to it, right? Reduce your sensitivity. Put earmuffs on, right? Right. Noise canceling headsets. Annoying friend canceling headset, right? So that's one thing you can do. You can reduce your sensitivity. What is the other thing that you can do? You can tell the person, say, well, cut it out. Yes. Right? Just reduce the source. Reduce your sensitivity, reduce the source, or the third thing, which may have been essentially the kind of combination of all that, reduce the coupling. Go sit somewhere else. Put a wall between you. Right? So reduce the coupling, reduce the signal source, or reduce your sensitivity to it. I can't think of anything fundamentally different. Now, when you say filtering, it's an interesting statement. You mentioned something about filtering earlier. Now, it's interesting because filtering implies that the signal that's bothering you is at a different frequency than what you're trying to operate. Now, if it's out of band, if it's in a different frequency, there are filtering techniques that you can play. But if it's inside your band, then the filtering tricks do not work as well. You need to do something more sophisticated. And there are other techniques, sophisticated filtering techniques that can help. But essentially, this boils down to this. So now, think about it. How can we reduce our sensitivity to the signal? And how can we reduce the impact of the source? So one of the things you can say, well, don't draw this line here. Draw it farther away. Sure. I mean, it would reduce the coupling a little bit, but it won't eliminate it. And if you have something that's quite sensitive, yes, these spikes may not be this large, they may become like half as large, but still they're large. What do we do? How do we reduce our sensitivity? How can we can you think of ways of reducing sensitivity and reducing the source if they are located in a given location? So the amount of coupling, let's say you've done all you could have done about reducing the coupling directly by placement and things of that sort. So now it's still not enough. What do we do? Can you think of a way? Yes?
Subtract a copy of the clock.
You can subtract a copy of the clock. So the idea here is that you're generating this clock. You might as well generate the opposite phase of this clock. And, well, I should have probably used a different color, but no, let's use a different color. So I can use the opposite phase of this clock and pass it exactly the same way around this thing, so I have the same sensitivity. Right? So you have two of these that are coupling the opposite amounts in the opposite direction into the signal, and you have to make sure that these are well balanced, right? This coupling. So you have to make this clockwise. Yeah, this could work. This could help to some extent. But you can imagine, you can start seeing that it's a little bit kind of a challenging thing to do in a systematic way. First of all, it means that anytime you're routing a clock, you're routing two lines instead of one. So your routing becomes more complicated. You have to drive two lines. And then you have to make sure that it remains symmetrical. So it's a good idea. And it does gives you some improvement. But let's say for some reason you don't want to carry two lines of clock, or you don't want to do things of that sort. So, but what else can we do? Yes?
If you have a capacitance coupling, you can use a conductor to help the coupling.
So you can create two couplings that cancel each other, right? That's what you're saying. You're saying you're using a second coupling to cancel the first coupling. In principle, that's possible. In practice, it requires a lot of detailed work, because then you're not talking about one or two lines. You're talking about a big chip. There are lots of digital lines going everywhere. It's not just one line. There are lots of data lines going across that are not even periodic, so everything needs to be modified that way. So it's a major overhead, and also a difficult analytical thing to do on a large number of things. Maybe if it's one line, yes. So what else can we do? Yes? Speak up, sorry. Have a separate ground plane with analog and digital. That helps, but that doesn't address this problem, right? The ground planes would be basically, if the coupling is happening through the ground planes and all those things, that's correct. But I'm saying that this coupling, I'm just saying that it's more direct. That's a good design practice. That's a good practice in design, but it's to address a slightly different problem. So what else? Can we do anything else? Shield it, well, which is basically reduce the coupling, right? So you put another metal layer here, separate them as much as you can, but how much shielding can you do? Because you have these metal lines parallel to each other on the IC, so you can try to make a tub, you can put it in there, but you add capacitance doing that. But yes, you can do shielding too. That's right. There was a measure against a copy of the coupling signal, so active cancellation, right? So these are all good ideas. So if you know what you're coupling into it, you can try to actively subtract it till it cancels, right? All of these techniques are good, but there's something that's even more basic and more fundamental that can actually help you a great deal, which is instead of taking your signal as one input, take it differentially as two opposite versions. So one way, for example, let's say if you have a patch antenna, you can take the output from both ends of this thing. Right? There are many different ways. If you have a dipole antenna, you can take these two inputs, and these two inputs will be in opposite phase. Now, in general, take the signal and break it into two equivalent parts that are in opposite phases, and carry those. So let's see what happens if we do that. So let's say now instead of doing this, we are going to have two lines. So my antenna is a differential one, and this signal has the opposite phase of that signal. So I take my signal, let's say Vin, and divide it into half in the positive phase. So I have what I call the VD. So let's say they have a VD. and I have two signals, let's say V1 and V2, whose difference is what I'm looking at. So what if I look at the difference of the signal? In other words, define VD as V1 minus V2. What if I take my information as the difference of two signals? What would that do in this scenario, in the coupling scenario? Well, you have this line passing by, and it couples to both of them, and it would induce the same kind of spikes on both of them. So what you have, let me just do a better drawing. So let's say this is one of the signals, and this is the other one. So let's say you have two signals that are going out of phase, but then you have a coupling signal, right? So you have spikes here and spikes there. You have spikes here and spikes there, spike here and spike there, so on and so forth, right? Now, both of these signals are experiencing pretty large amount of interference. But what if I look at the difference of these two, V1 and V2? The difference of these two, what the interference is, the interference appears as something that's not in the difference, right? It's common to both of them. We call them common mode. It's common to both, and as a result, what happens is that if I plot V1 minus V2, I'll see something like that with very little interference. So what if I could carry all of my signals in differential form, or basically as difference of two different things? For that to happen, I need to have an amplifier that can amplify these things in a pair. So what is the simplest form of making that amplifier? We can do a variety of different versions. So let's say I have two signals coming in that are going in opposite phases, and I want to amplify them and keep them differential. So what do I do? Well, you can make an amplifier here, right? You can make an amplifier like this. Let's make a common emitter amplifier or common source amplifier in a MOSFET. Right? Let's say we had something like this. So this is RD. So this is V1 or VI, and then this is V in 1, I1, and VO1. Right? And then I can actually apply this one to another amplifier, just like that. VO2, VI2. So what happens is that both of them get amplified, and you get some amplification here. Oh, it's going to be an inverting amplifier, so if I want to kind of like remain faithful to those waveforms, you will get some amplification here. Now, sure, I can do that. Did I solve the problem by doing this? Did we solve the problem? In other words, if there were spikes here, let's say, so there was a spike here, there was a spike here, there's a spike here, spike here. Did we eliminate anything by doing this? No, right? Because the spikes will go through the amplifiers. Probably they will saturate the amplifier now, because this spike is now going big here, and this spike is going big there, and then this spike is just messing this up here, and this is going to mess it up here. Right? Intuitively, kind of like just qualitatively looking at it. So we haven't solved this problem. We just amplified both of them. And yes, you can say, oh, you can look at the difference of these two, still would be good. It would be good if these were amplifying linearly, right? If there's some nonlinearity, then the subtraction is not going to work anymore. So I haven't really improved the situation. I have created two lines, but I don't have a good way of amplifying it. So what are we looking for? What is the quality of behavior of the stage we need to do this thing? We need something that amplifies this, I don't know, blue thing, the signal, and actually suppresses the red one. Can we come up with something, a stage? Can we modify our stage and design a stage? So we are going to go through the thought process of the design of the stage that would amplify the blue and attenuate the red. So what is different between the blue and the red? So if this was V1 and V2, right? Blue is captured as V1 minus V2. We show it as VD, V differential. There's another component. We can call it VC, the common mode, which is V1 plus V2 over 2. So if I just look at V1 minus V2, what do I see? Do I see less of the red or more of the red? Less of the red, right? I see more of the blue. So this one is going to generate more of the blue. And this one is going to be more of the red. Because now the blue is going to get suppressed because they are opposite phases of each other. They're going to cancel each other, but the red stuff is going to add. Right? So we want to make an amplifier that amplifies this and suppresses that. The situation right now what we have is that they both get amplified equally. So why is that? If you think about these things, the red stuff, how does it appear? Let's think about it for a second. Let's think about these voltages as actual heights. Let's say the two ends of this thing represents they represent the voltages, V1 and V2, right? So this is V1, let's say this is V2, right? For the blue stuff, what's happening? One side goes up, the other side goes down, right? You see a seesaw operation. For the red stuff, what do you see? You see a common mode operation. So what happens is that when these two inputs go up, you get gain. Why do you get gain? What is the gain up mechanism? As this voltage goes up, your VBE is going up, your current is going up, you draw more current through the resistor, right? And therefore you lower the voltage, you get amplification through the exponential. So we want to create a situation that when these two go up together, the total current, the current in each one of them doesn't go up. How can we enforce that? How can we enforce that if both sides are going up together, the current is not going to increase? The current of either one of them is not going to increase. Have a common current source, right? So if they share the current source, if I take these two and put them side by side, I'm going to flip one of them left and right, and have them share the same fixed current source. Then what's going to happen if both inputs go up to the total current in the collector? So let's say I take these two and push them up together. If this is an ideal current source, the sum of these two currents have to be IE. And if I push them up together, there's not going to be a difference between them because they're symmetrical, at least the way I've drawn them, right? So both of them go up. This voltage goes up, but this current does not increase. So this current is going to be half of that current. The emitter currents are going to be half of that, and it's going to be alpha times half of that. So that current is not going to change. So is there going to be a change on this voltage? No, right? Because this terminal goes up, the total current remains the same, therefore the current through the resistors are the same, and this voltage is simply, what is this voltage? It's basically VCC minus RC times IC. If IC doesn't change, that voltage is not going to change. So what does it do to the red stuff? It doesn't amplify it, right? It actually attenuates it. How about the blue stuff? Does it do anything to the blue stuff? Well, if this side goes up and this side goes down, right, then there would be current, more current going in this direction and less current going in this direction. So the current is steered in this direction, and as a result, this voltage will go down and this voltage will go up. So this stage produces differential gain and common mode attenuation. That's why this stage is made instead of this stage. This is the fundamental understanding of it. Basically, this current source is critical. And you can see how much, if I ask you right now, before we write any equations, how much this common mode rejection depends on, how much would it depend on, what would it depend on the most? Let's wait, not how much. This common mode rejection, what would it depend on the most in terms of the properties? What parts of this stage are most responsible? The quality of what part of the stage is most responsible for how much common mode rejection you get You should be able to answer that question before I write any equations. How good is this current source, right? Because if you make this an ideal current source, this would be completely suppressing. Now, if this were not an ideal current source, if you had some output resistance, as you increase this, you get a little bit more current because there would be some extra current going through that resistor. So you will get some amplification of the red stuff. So the quality of that current source would determine your common mode rejection ratio. And these are the insights you need to have to develop and expand on before you write equations. And also you need to understand the thought process of how you arrive at this stage. This stage was first invented in vacuum tubes, actually. It was used with vacuum tubes, the differential pair. And of course it has been reused. And it's perhaps the best, the greatest of all of the two transistor stages because it has a lot of interesting and good properties. But this is the most essential property that we're talking about. So something like this would be very interesting to work with. But let's now analyze it. Let's actually write equations and see how it behaves. We can do it for bipolar, and then we'll do it for MOSFET next time. So you have something like this. Let's understand how it does. So there are really two things in this. There is a differential operation and common mode. Let's start with the differential operation because that's really the desired operation. So let's say you have an input that's V1. So you have two voltages, V1 and V2, right? If you have any two voltages, actually, as a matter of fact, you can always decompose them into VD and VC, right? Because you can write these two things. For any arbitrary two voltages, you can write a common mode part and a differential part, defined as these. And therefore, you can actually express them in those forms. So this is actually equivalent, and we'll see it in a second, of being VD over 2 and negative VD over 2 and a VC. So this combination, from the perspective of these two terminals, behaves exactly the same as this combination. Because if you look at that, what does it generate as? So let's look at what you get on this terminal. You get VC plus VD over 2, right? If you calculate VC plus VD over 2, what do you get? Well, VD over 2 is V1 minus V2 over 2, and VC is V1 plus V2 over 2. So you add them, you get just V1 over 2 plus V1 over 2. So this becomes V1. And the same way, VC minus VD over 2 is going to be V2. Very simple. You can solve for them in terms of VC and VD, right? So you can think of any two arbitrary sources, really, as a combination of a differential part and a common part. The sum and the difference and the sum. So let's focus on the difference for now first, and then we'll get to the sum part in a sec. So let's say you have something like this. Let's say you have, so essentially it's like saying that you have a VID applied here. And somehow you maintain the base bias. If this bothers you, we can keep it this way. VID, differential input, over 2 and negative VID over 2. So this would be the same thing. So basically I'm setting the common mode to ground. I need to maintain some voltage. I need to have some operational voltage for this to work. Well, if this were an ideal current source, you wouldn't. But let's say this bias. Let's not worry about biasing for now. So you have, what is the voltage across here? What do you see? The voltage between these two input terminals. What is that voltage? VID. By definition, it's V1 minus V2, right? So I'm trying to find what's the relationship of the output currents, let's call this IC1 and IC2, to the VID. Even more interestingly, I'm interested really in delta IC, which is IC1 minus IC2. Because it's that difference that induces the differential voltage at the output. So we are trying to calculate that in terms of VID. So what we are trying to do is to find the functionality of, we want to show this as a function of VID. And we'll do the large signal one first, and then we'll get to the small signal later. But let's do the large signal. Let's do the nonlinear analysis first, because it's worth doing it here to see how it behaves. So what do we get? Well, I need to understand what IC1 and IC2 are, right? So what do I know about this bipolar transistor? I know that this is a VBE1 and this is VBE2. So we know that VID is VBE1 minus VBE2, right? KCL around this loop. This voltage minus that voltage is VID, the difference between these two. Okay? All right. So that's VID. And then, but what do I know about VBE1 and VBE2? How are they related to IC1 and IC2? Well, the exponential transistor behavior, right? It's the relationship between the IC and VBE. So isn't it true that VBE1 is VT natural log of IC over IS? This is another way of writing this. IC is IS e to the VBE over VT. We are ignoring the early effect for now, right? So that's the exponential. This is the inverse of the exponential. So this is IC1 over that. And then VBE2 is going to be VT natural log of IC2 over IS. And of course, you're subtracting two logs. What do you get? So VID is going to be VT natural log of this divided by that, the argument, which would be basically IC1 over IC2. Now, there's an assumption that we've made here when we wrote this. Essentially, when I canceled the IS's, what assumption did I make? They are identical, right? That these two transistors have the same IS, which means that they have to behave very exactly the same. So the matching of these two transistors matters. If they're mismatched, it would be a problem. And we'll talk about this later in more details. So the matching of these two is important, because otherwise this could not be done. So, of course, you can take this and you can invert it. So you can write it as IC1 over IC2 equals e to the VID over VT. This is the thermal voltage. OK? So that is OK, but I still haven't gotten to this. I'm trying to find what's the relationship between the difference of these guys. Is this the only thing I know? IC1 over IC2 is exponential. So I know that the ratio of IC1 to IC2 is an exponential. Right? What else do we know about IC1 and IC2? Do you know another relationship between IC1 and IC2? Well, let me ask you a question. Sorry, go ahead. Go ahead. There was somebody. There's some. Well, we really know that the sum of these two, IE1 and IE2, is what? If you have an ideal current source, IE1 plus IE2 has to be IEE, right? So basically we say IEE is IE1 plus IE2. But we know the relationship between IE1 and IC1 if the transistor is in forward active region, right? Which is what? How are they related? Alpha, exactly. So this is basically this divided by alpha, or in another way, basically saying IC1 plus IC2 is alpha IEE. So now you have two equations for these two, right? So you can actually find what IC1 and IC2 are in terms of VID. So for example, if I factor IC2 from this thing, so I get IC2 times 1 plus IC1 over IC2, right? And I know this is alpha IEE, is going to be, and this term, we already know it's exponential, so it becomes IC2 1 plus the exponential e to the VID over VT. So from this, we can calculate IC1 and IC2. So IC2 from this is simply alpha IEE divided by 1 plus e to the VID over VT. And likewise, you will get an IC1, which is alpha IEE, 1 plus e to the negative VID over VT. Right? Does that make sense? And if you plot these, what you will see, if you actually look at it versus VID, it's relatively straightforward to plot these, right? Because what you have you can see, so this is, let's say this is VID, and this is IC1 or IC2. So when VID is 0, there's no differential voltage. What do you get? This exponential is 1. This is 1, so you get 1/2, 1/2. So you're going to be at half of alpha IEE. Both of them. Now, as you increase VID, let's say you make it positive, this denominator becomes larger, right? And therefore, IC2 becomes smaller, and IC1 becomes larger. So this is IC2, let's say, and then let's say this one is IC1. So this is IC2, and that one is IC1. Now, it doesn't take that much voltage to switch this almost completely, because this is an exponential, right? If the VID is let's say 3 VTs, you have e to the power of 3, right? It's a pretty large number. It's greater than 10. So you have 1/10. So by the time you're at 3 VTs, which is basically like 75 millivolts, because VT is about 25 millivolts, right? In bipolar. By the time you're at 75 millivolts, maybe 100 millivolts, you're almost completely switched to one side or the other. So it switches quite rapidly, if you think about it. Now, these are good, these are useful, but we still haven't calculated one of the key things, which is what we wanted to calculate was the difference between the ICs. We wanted to calculate the delta IC, which was IC1 minus IC2, right? Up there, we defined it. So we want to find the functionality of that as a function of VID. So we need to do a little bit of an algebra, right? So what we need to do, we take these two. So we have a common part, alpha IEE. So what you have is that you have 1 over 1 plus e to the negative VID over VT minus 1 over 1 plus e to the positive VID over VT. And then what is that? Well, there's a little bit of a manipulation we need to do. I will factor half of this and half of that from the denominators. So when we do that, you get alpha IEE, okay? And then half of that would be e to the VID over 2VT times, now if I factor it out of this one, negative VID here. So I would get e to the positive VID over 2VT plus e to the negative VID over 2VT. Then I will, similarly for the other one, it would look like this. It's a little bit of a mess here, but bear with me. So factor half of that, VID over 2VT. Then you get e to the half negative VID over 2VT plus e to the positive VID over 2VT. So this was the worst part. Now you recognize this is common between both of them, right? So we'll factor that out. So we are going to have alpha IEE divided by e to the positive VID over 2VT plus e to the negative VID over 2VT times whatever is left. What is left? So it's going to be 1 over e to the negative VID over 2VT minus 1 over e to the positive VID over 2VT. Okay? Now, we need to form a common denominator. What's the common denominator of these two? 1. So then you have alpha IE divided by e to the positive plus e to the negative of that thing. So what we are left with, this is going to go here, this is going to go here. So it's going to basically be, I'm going to put them in the denominator. So you get e to the positive here minus e to the negative here times alpha IEE, When I say negative, I mean negative VID over 2 VT. I'm not just showing it. And this has a name, this function, right? What is it? Yeah, hyperbolic tangent. So it's basically alpha IEE hyperbolic tan of VID over 2 VT. So that's the differential current, large signal differential current. The large signal describing, the function describing this is going to be a hyperbolic tan. So if I want to see actually what is delta V out, the differential voltage, VO2 minus VO1 minus VO2, I have to write each one of them in terms of ICs. Right? So I can write this as VCC, the first one is VCC minus RC IC1 minus VCC minus RC IC2. Right? You can see that the VCCs cancel. And then what you're left with is RC. So you get negative RC delta IC, which is going to be given by that. So it becomes negative alpha RC IEE tang of VID over 2 VT. So that's the large signal characteristic. The relationship between the differential output voltage and the differential input voltage is given by that. Now, that you can actually show, again, hyperbolic tan behaves like that. So if you look at the differential input, we can call it VOD, it behaves like this. And at some point, basically after 3 or 4 kT, it basically saturates. Okay? Now, what we'll do next is to look at this large signal behavior and look at the small signal equivalent of this circuit. And you'll see different ways to analyze it and simplify it to think about these differential stages. And these differential stages are very critical to a lot of design for a variety of reasons. One is that because you have the differential signaling and suppression of the common mode signal, so you can actually get a lot less sensitivity. And this is important if you are putting a lot of stuff very close to each other on a chip. The other thing that's very interesting is that these stages are very conducive to being cascaded without having to have DC level shifters, which is another strength of these differential signaling. And that enables you to basically make a cascade of these differential signals and have them do certain kinds of operation for you. So we'll use them a lot, we'll deal with them a lot, we'll have a lot of variations of that. But that's the core essential behavior of the bipolar one. We'll do a similar thing for MOSFET next time. And then we will see, in general, if you have an arbitrary 3-terminal device, what are the things that you can say or you cannot say about it based on the differential operation. Okay, any questions? All right, thanks.